Hi, I'm Dylan from the Economics Tutoring Center at Arizona State University. So today we're going to be working on Lagrange. If you have any questions about the Lagrange, firstly, it's actually going to involve some first order derivatives. So if you have questions on those, we actually have another video on those in our playlist. So go ahead and review that before you do this. So today we're going to be looking at our long-run cost minimization. The first step to doing that is we actually want to write our cost function. So in this case, we get to assume this production function, and we also have our WK and our WL, which are constant. So when we write our production function, or we write our cost function, that's our cost is equal to our amount of capital times our cost of capital. And we also add our amount of labor times our cost of labor. Okay, so we have our cost function. Now what we got to do is we have to set up the Lagrange. Now, remember, a lot of people make the mistake doing the Lagrange for producers. When we write a Lagrange, we have to remember that it's the optimal function minus the lambda times our constraint. Now, a lot of people, when we do the Lagrange for producers, will be tempted to put our production function in for our optimal, and we'll be tempted to put our cost function in for our lambda, because our cost function looks like our budget function, which we put here for consumers, and our production function looks like a utility function, which we put here for consumers. But we have to remember that with producers, the cost function is going to go here because that's where we're optimizing. Production function is going to go here. So go ahead and write it out. So it's our cost function, that's WK times K plus WL times L. This can be a plus or minus lambda. I prefer to use minus just because the algebra works out a little nicer. And this is going to be times y minus the production function. We have it written out like this, and so now we have to take our three first order conditions. This is where we're going to be doing our first order derivatives. So the first one we do is going to be in terms of k. The first derivative in terms of k is multiplied by a constant, so it's just going to be WK. Our second one is lambda times this function, is the term we're interested in. And so what happens with the k, remember the power rule, the a comes down, this becomes a minus 1. So we have our plus lambda times 2 times alpha, and then k to the alpha is minus 1, L to the beta. And remember, since it's our first order condition, we're doing an optimization, this has to all be equal to 0. We can do the same first order conditions for our L value. So d lambda dl is equal to WL plus lambda. It's going to be pretty much the same except we're bringing down a beta, and it's going to become beta minus 1. So times 2 times beta, k to the alpha, L to the beta minus 1. And that's all equal to 0. And now lastly, as a formality, we're going to go ahead and take our first order condition in terms of lambda. This is just going to get us to what looks like our cost function. So we go ahead and get is going to equal y minus 2k alpha L to beta. And that has to be equal to 0. So this is basically saying it's just restating our production function with our first order condition. Okay, now that we have these, we're going to go ahead and use these two equations to try to set our marginal functions equal. So with both these, what I'm going to do is, because I have an addition sign to each of them, so I want to bring one of these terms from each of the equations over to the other side, like so. I'm going to get WK equals negative 2 lambda alpha k to the alpha minus 1 L to beta. See, I just went ahead and brought over this term to the other side of that equation. And then I have my WL equals negative 2 lambda beta k alpha L to the beta minus 1. Okay, it looks a little bit intimidating, but it's actually going to cancel out pretty nicely. So remember what we do when we get to this point in the Lagrange is that I'm going to take this left side and divide it, and this right side and divide it. So it's going to be WK divided by WL is equal to all this divided by all of this. So well, you notice a lot of things are actually going to cancel out. So our negatives cancel out, our 2's, and our lambdas. What we also have is we have k to the alpha minus 1 up here, and just k to the alpha down here. So the k to the alpha minus 1 will completely cancel out, and this alpha goes away. Likewise, this L to the beta minus 1 completely cancels out, and this beta goes away. What I end up with is I have WK over WL is going to equal A times L, B times K. Okay. Now what I do is I want to go ahead and isolate one of these. In this case, I'm just going to isolate L. So what I end up getting is I get L is equal to WK beta over WL alpha all times K. Now, this is not our L star because remember we can't have our L star in terms of K. So we're not quite there. What I can do though is I can just plug this in, this whole thing, for L in this equation. It's going to look a little messy, it'll get nicer though. So I end up and get y minus 2 k to the alpha WKB alpha times k all to the beta. Remember what we did there is we went ahead and brought this L value and replaced this L in here. And that's how I got this. Remember I had to set this equal to 0. Okay. Now what I want to do is I want to isolate that k value, because if I can do that I can find my k star. Now with algebra techniques I can go ahead and combine these two k's. This k is raised to the alpha, it's being multiplied by this k raised to the beta. And so if I go ahead and just multiply those together, I'm going to get k to the alpha plus beta times this whole block and that's equal to y. I'm just going to go ahead and bring over the y on that step too. So what I can do now, I want to go ahead and isolate this k. To do that, I'm going to go ahead k alpha plus beta equals y divided by all this. I'm going to isolate this k. I'm going to go ahead and I'm going to want to bring everything to the 1 over alpha plus beta. And it's actually going to be my k star too. There's a beta there as well. Okay, looks kind of messy. Fortunately for us, you're normally going to go ahead and you're going to have your variables, so you can just plug them in at that point. Now, we have our k star. We don't have our L star yet. What we can do is we can actually just plug in this k star right into this variable. And it'll go ahead and that'll give us our L star. I'll just review this real quick. What we did, we have our cost function, we set up Lagrange to call our first order conditions. Once we have these two first order conditions, we can use that to set the marginal rates of substitution equal. We can use that to find our L star and our k star. We'll go ahead and erase a couple of these things now. So when I find my L star, I'm going to take this equation and I'm just going to go ahead and plug in my k star. So that's going to be WK over all that times my k star Okay. Now, once we have our k star and our L star, you're pretty much done finding the optimal cost minimization. So what I do with these is I take this, and I take this, and I just plug those in for my k and my L. I could write it out for you if you like. So C equals WK, and I'm just going to write k star, you can replace that if you'd like, and then my WL times my L star. Okay. So, just to review, once we did our first order conditions, we went ahead and we used algebra techniques to find our k star and our L star, Once you have those, you just plug them into your C value. And that is how you do the long-run cost minimization for producers. Hope this helped. If you have any questions, go ahead and come to the Economic Tutoring Center at ASU.